Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part 4 of the lecture on flood frequency guidance, Bulletins 17B and 17C. In our outline, we're down here at the expected moments algorithm, or EMA computation. So the EMA computation actually isn't any different than we've seen before when there's only point data involved. So if we have no low outliers or historical information and no flood events specified as intervals, then all we have is point data. And we can estimate the moments based on the product moments of the sample, as we've been doing, right? So these are the sample product moments that we've been using for the last 2 days. The real innovation in the expected moments algorithm comes from dealing with interval values, right? So you can imagine if we knew our population moments, then for any of those interval observations, we'd be able to compute the expected mean, standard deviation, and skew of the intervals, right? The moments of the intervals. So if we knew our distribution parameters, we would be able to specify the interval. The area under the curve would allow us to compute the expected moments, right? On the other hand, if we already knew the expected moments of those interval observations, we'd be able to use them to estimate the population moments, right? Which is the direction we really want to be going. So what we really want to do is estimate the population moments, but unfortunately, we need to start with them. So what we do is do an iterative procedure where we start with an initial guess of the population moments, and we go through step 1 and then go through step 2 and see if we end up with the same, and we iterate until they converge. Right? Now, this is a computation that is better not done by hand. There's some examples of doing it in a spreadsheet with an extra tab for each iteration, but mostly we're pretty happy to let the computer code iterate for us. Okay, so moving on to weighted skew and confidence intervals. Both of these are related strongly to the uncertainty in skew. So weighted skew. As I've mentioned, there's a lot of uncertainty in the estimation of the skew coefficient from a sample. Even when it's a representative sample, a small sample is going to have a lot of volatility in the estimate of skew. So GS, the station skew, is just the skew coefficient estimated from the sample of annual maximum flows at the station. To help with this, we bring in a regional skew coefficient, right? So a regional skew is one that's estimated by bringing in other gauges in the region and doing something called trading space for time to have a larger sample and therefore get a more accurate skew coefficient estimate, but it's less specific to our particular site. And we don't want to lose the skew coefficient that might be more specific to our site than some other sites in the region. So the approach taken is to weight the station skew with the regional skew. Now, each estimate of skew has some accuracy and so has some mean square error. So what the weighting does is it weights the station skew here by the inverse of the mean square error of its estimate. So the larger the mean square error, meaning the less accurate the equation, the lower the weight will be. And it weights the regional skew by the inverse of its own mean square error. So what will happen here is with a smaller sample, there'll be more error in the station skew, meaning a larger mean square error. And so the station skew will then have a lower weight against the regional skew in the weighting formula. And with a longer record station, the station skew estimate is going to be more accurate and have less error, and then the station skew will get a larger weight in the formula against the regional skew. So the regional skew will have kind of more power when weighted against a shorter record station, and it will have less power when weighted against a longer record station. Now, we actually have a slightly simpler looking version of the skew weighting equation that comes from simplifying a little bit, but note that in the simpler version of the equation, the mean square error of the station skew is multiplied by the regional skew, right? Because we've gotten rid of the 1 over m, so you have to be a little careful with that. Okay, so moving on to confidence intervals. So we use confidence intervals to demonstrate the uncertainty we have based on sampling error. So this is where we're capturing the fact that we think our samples might not be representative. So we often show a 90% confidence interval around our frequency curves. Although USGS software, I think, defaults to a 95% confidence interval. So I think I've mentioned that the confidence interval formulas in Bulletin 17B are actually based on a log normal distribution. And the log normal distribution has a 0 log space skew that isn't variable. So there's no parameter for skew coefficient in the log normal distribution. And if there's no parameter, then the uncertainty or the confidence intervals around that distribution won't recognize the uncertainty in skew. They can only recognize uncertainty in the parameters of the distribution, right? So what happens then is that those confidence intervals are going to neglect the uncertainty in skew coefficient. And as we've said, the uncertainty in skew is pretty large. Right, the expected moments algorithm confidence intervals do include uncertainty and skew, right? So they are going to be a little bit wider. Those confidence intervals for EMA also reflect the historical information and the low outlier information, because within the expected moments algorithm, all those computations are done simultaneously rather than one at a time as they're done in the Bulletin 17B approach. Right? So the difference in the confidence intervals would be very small for a skew coefficient of 0, for a log space skew coefficient of 0. And as skew gets further from 0, the differences will increase. So here's a data set with a slightly positive skew. Now this again is only point values, so we have no low outliers and no historical information. So the 17B and 17C computation is going to give us the exact same log Pearson 3 distribution shown in red. But the Bulletin 17B confidence intervals are in green, and we can see that the Bulletin 17C confidence intervals in purple are wider, right? And now this is a fairly minimal positive skew. I'm going to show an example with a bit of a larger skew. This is a skew coefficient of almost 1, right? So here's another sample that has no outliers and no historical information. Although seeing this large value makes me want to go seek some historical information. But at this point, it doesn't have any historical information or low outliers, and so there's no intervals. And so Bulletin 17B and 17C are going to get the same resulting log Pearson type 3 distribution shown in red, and the 17B interval is in green, the 17C interval in purple. And as you can see, they're quite a bit more different when the skew coefficient is so large as almost 1. So I decided to do a little demonstration of the differences in these confidence intervals based on the uncertainty and skew. So you haven't yet seen the videos for the uncertainty in frequency analysis lecture, but I'm going to give you a little bit of a preview. So I did a sampling experiment where I computed the uncertainty based on a sample size of 107. So I started with the original estimated curve and drew a random samples of size 107 from it and re-estimated the log Pearson type 3 distribution, plotted it as a gray line, and then did that again with another sample of size 107. Okay, and from that random sample also fitted an LP3 distribution. Doing that hundreds of times, I got all of these gray lines. And as you can see, they really span the 17C confidence intervals to demonstrate that our uncertainty from sampling error is really that large. And then I repeated the experiment with the Bulletin 17B situation, meaning not recognizing the uncertainty and skew. Right? So if I did the same experiment, but I only recomputed the mean and the standard deviation from the samples and did not recompute the skew, but always left it at 0.96, then my curves look like these. These gray lines are spanning only the Bulletin 17B confidence intervals, but not the 17C. So this is showing that it does look like a lot less uncertainty when we don't recognize the uncertainty and skew, but we also know that that isn't the right thing to do. So just to summarize the uncertainty descriptions, the Bulletin 17B intervals use what's called the non-central T distribution, which is something we'll see in the uncertainty lecture, but they are based on the log normal distribution, and so they don't consider the uncertainty and skew. The Bulletin 17C intervals do capture the uncertainty and skew, and so they are therefore more correct and generally wider than those from 17B. So finally, what things does Bulletin 17C still not address? Well, variables other than unregulated instantaneous peak flow aren't addressed. We have all of these other variables that we'd like to do frequency analysis on. Now, In some ways, it is better not to have federal guidance, better not to have someone telling you exactly how to do your analysis. So we kind of like the freedom with these things, but the study that goes into generating the federal guidance can be really helpful in finding the best ways to evaluate these variables. So we will work towards having guidance on these. Okay. Other things that aren't yet included are flood frequency curves in ungauged areas, meaning we don't even have data, regulated flows where analytical distributions don't really fit, and then when the assumptions about homogeneity, reliability, and randomness are challenged. So the homogeneity assumption we also call the stationarity assumption, since our data is collected over time, and maybe the watershed is not really unchanging across time. Right, so 17C does recommend tests for trend and change, and if trend or change is detected, there is allowance for other methods. And one of them is maybe time varying parameters instead of constant parameters for the whole period. But more work is being done on these topics, and as good methods are developed and tested, they'll be included in later guidance. Right, so that was the end of which video are we on? That was the end of video 4, and thank you for hanging with me.